Number 1, consider the polynomial p of x. Find p of 4 in two different ways. So the way before you would find p of 4 before you learn this lesson was plug in a 4. P of 4 is 4 cubed plus 6 times 4 squared minus 8 times 4 minus 1. That's 64 plus 16 times 6 is 16 times 6 is 60 plus 36. 60 plus 36 is 96. Minus 32 minus 1. That gives me, add these together, use your calculator, don't make a mistake, is 64 plus 96 minus 32 minus 1 is 127. So P of 4 apparently is 127. How else could I find it? Well, this would be the same. P of 4 would be the remainder when I divide by x minus 4. So if I divide by x minus 4, my remainder is going to be P of 4. So we start the long division and say, what times x gives me x cubed? X squared times x is x cubed, and we multiply through. Change your signs to subtract, and we get 10x squared minus 8x. What times x is 10x squared plus 10x? 10x times x, it's now 6 period. 10x times x is 10x squared minus 40x. After you multiply, change your signs to subtract, and we get 0 and positive 32x minus 1. What times x gives me 32x plus 32? 32, multiply through 32 times 4 is minus 128. Change your signs to subtract, and you're left with positive 127, which makes sense because our remainder was the same that we got when we had P of 4. So this is the remainder theorem at work, saying if I want to know what P of A is, I divide P by x minus A. The remainder is the function value at that point, A. Number 2, is x plus 1 a factor of this polynomial? Well, there's two ways we can do this. We can divide, but that would be a lot of work. If x plus 1 is a factor, we know that x plus 1 is a factor if and only if x equals negative 1 is a 0. Because if I plug in negative 1, that will be the remainder of my division, and I want a remainder of 0. So let's plug in the negative 1 into our function here. P of negative 1 is 2 times negative 1 to the 5th, minus 4 times negative 1 to the 4th, plus 9 times negative 1 cubed, minus negative 1 plus 13. This result will be the remainder if I was to divide by x plus 1. That gives me negative 2 minus 4 minus 9 plus 1 plus 13. That gives me minus 6 minus 9 is 15, minus 15 plus 14. That gives me a remainder of negative 1. P of negative 1 is negative 1, which means that the remainder is negative 1. So x plus 1 is not a factor. X plus 1 is not a factor because the remainder is not 0. The remainder is negative 1. Number 3, find the value of k so that this quotient has a remainder of 16. So I want to have a remainder of 16. I think you could do this by doing long division, but that would be a mess. So if I divide by x plus 2, that means if I plug in a negative 2 for x, the value of that is going to be the remainder. So if I say I'm going to plug in a negative 2 for x, that function's value at negative 2 will be the remainder when I divide by x plus 2. And I want it to be 16, so I'm going to set it equal to 16. It gives me negative 8k minus k minus 2 equals 16. So negative 9k, I'm going to add 2 to both sides, equals 18. equals 18. So divide by -9 and get k equals -2. So for this to have this quotient to have a remainder of 16, we would want k to be -2. Using the remainder theorem here is a very powerful tool to quickly find out that value of k. Let p of x be this function. Verify that p of 9 equals 0. Well, let's do that first. That means if I plug in a 9, I should get out a 0. 9 cubed minus 8 times 9 squared minus 29 times 9 plus 180. What does that give me? If I go over to my calculator and type that in, 9 cubed minus 8 times 9 squared minus 29 times 9 plus 180, that gave me 0. So that tells me that x equals 9 is a 0 of this function. X equals 9 is a 0. Well, using the factor 0 theorem, if x equals 9 is a 0, x minus 9 is a factor. So express p as the product of 3 linear factors. Well, x minus 9 is one of them, so let's find the other 2 by actually dividing. I'll do reverse tabular for you reverse tabular people out there. That has to give me x to the third. That needs to give me -8x squared, -29x, and that has to give me 180. Well, x squared times x is x cubed. I'm going to multiply through now. I want -8 of them, but I have -9 of them, so I'm going to add a positive 1 there. Plus x. X times -9 is -9. X. I want -29 of them, so I'm going to have to add another -20x. -20 times x is -20x, and this works out because I have a remainder of 0, which also verifies that x minus 9 is a factor, which means x equals 9 is a 0. So p of x is x minus 9 times, if we thought of this as a multiplication question, times x squared plus x minus 20. Well, that's not 3 linear terms, that's 1 linear term and a quadratic term. So x minus 9 times what? Well, this is a trinomial with a leading coefficient of 1, so we can do this quickly. What multiplies to -20 that adds to 1, plus 5, and minus 4. So p of x, in factored form, is x minus 9, x plus 5, and x minus 4, the product of those. When does p of x equal 0? P of x equals 0 when this equals 0. So that happens at x equals 9, x equals -5, and x equals 4. These are the zeros of p of x. We found the zeros. That's what solving the solution, that's what finding the solutions to that equation is. That's kind of putting this whole unit together of using the remainder theorem, the division, factoring, and finding zeros, because now we could graph this function quickly by using end behavior and those zeros. Number 5, explain why x to the 51 minus 21x plus 20 is divisible by x minus 1. If you did this by long division, your long division would have to be 52 terms long. That's insane. Use the remainder theorem. If x minus 1 is divisible, if this polynomial is divisible by x minus 1, then x minus 1 would be a factor, which would mean that x equals 1 is a 0. So using in the remainder theorem, if I plug in a 1, I would get 1 to the 51 minus 21 plus 20. So that gives me 1 minus 21 plus 20. That sum is 0. So the remainder, when I divide by x minus 1, is 0, which means it's a factor, which means it's divisible. So using the remainder theorem and showing that p of 1 equals 0 tells me that x minus 1 is a factor. The remainder theorem tells us the remainder is 0 when we divide by x minus 1, which makes it a factor. Number 6, explain why for a polynomial function p of a is equal to the remainder of the quotient of p in x minus a. So this is kind of just talking about the idea of what is the remainder theorem. The remainder theorem says is if I divide p of x by x minus a, I can write it as some quotient function, I don't know what it is, plus the remainder over x minus a. I know that remainder is going to be a number because if it was a linear term, I could still divide it by x minus a, so it has to be a plain old number. If I multiply both sides, if I multiply everything by x minus a, I get q of x times x minus a. Sorry, not q of x minus a, q of x times x minus a plus r, because that divides out, that needs an x minus a term, and that divides out there if I was to actually multiply both sides by x minus a and use the distributive property. So p of x can be written as this quotient times x minus a plus this remainder. So if I find p of a, that's going to be q of a. I really don't know what that is, and I don't care because I'm multiplying it by a minus a. A minus a is better known as 0. So this is p of a times the quotient at a times 0 plus r. Well, 0 times anything is 0, which leaves me with p of a equals r, which is my remainder. So this is kind of just going through the proof of the remainder theorem. Will you ever have to do this? No, but you should know where the remainder theorem comes from. It does not fall from the sky. Steps. Write a formula for a possible polynomial function that the graph represents using k as the constant factor. So this is using the factor zero theorem. If those are my x-intercepts, what are my factors? Well, my polynomial, I'll call it p of x, could be x plus 4, it's degree 5, and I have 5 x-intercepts, so they're all multiplicity 1, x plus 2, x minus 1, x minus 3 times x minus 5. But there's infinitely many polynomials that have those zeros because I can just change the leading coefficient. I can change the leading coefficient there. So suppose the y-intercept of the polynomial is negative 4. So when x equals 0, y equals negative 4. Find the value of k. So now we can use this extra point to find the value of k. So when I plug in a 0, plugging in a 0 for x, it should give me a negative 4. I can now solve this equation for k. A lot of you get tempted to start adding all these numbers over here. Don't add them because they're all being multiplied. 4 times 2 times negative 1 times negative 3 times negative 5. Use your calculator. Don't make a mistake like that. 4 times 2 times negative 1 times negative 3 times negative 5 is negative 120. So negative 4 equals k times negative 120. How do I get k? I divide. 4 divided by negative 4 divided by negative 120 is 1 over 30. So I can go back up here to part A now and change that k because I know that k has to be 1 over 30. And that's the specific polynomial function that passes through that y-intercept. I could have given you a different point and you would have found a different leading coefficient. Consider this polynomial. Factor it completely. So I don't like that negative leading coefficient there. So I'm going to factor out a negative, and my GCF is x squared. I'm going to factor out a negative x squared and get left with x squared plus x minus 6 equals p of x. Well, that's negative x squared times x plus 3, x minus 2. That's a trinomial. Factor that. That's factored completely. Sketch a graph of p without using a calculator. So these factors will tell me the 0. What are the zeros of this function? There's one at 0. There's one at negative 3. And then there's one at positive 2. The multiplicity of 0 is 2. That has multiplicity 2. So it's going to be tangent to the x-axis. It's going to touch it and then turn around. We need to look at the end behavior. It's an even degree polynomial with a negative leading coefficient. So if you're going through the dance right now, it's the second one. So it's going to have that type of end behavior. So I'm going to go through and graph it now. Cross this through. It's going to turn around and touch that. And it's going to cross through again and go down to negative infinity. That's using all of those ideas of zeros, factoring, multiplicities, and behavior. We can use all of those ideas to graph this function. Check it on your calculator, make sure it looks something like that. Find this quotient using 2 different methods. Well, this looks like one that I can quickly do by inspection. I want an x minus 6 up top, so without changing the value, I'm going to have a minus 2 also in the numerator, because that's the same thing as x minus 8. This gives me x minus 6 divided by x minus 6, minus 2 over x minus 6. 1 minus 2 over x minus 6 is the quotient. You could also do this by long division, with a short long division, so I'll do it. 1 times x gives me x, subtract, and I get a remainder of negative 2. So my answer is 1 minus 2 over x minus 6. Inspection, I think, is a little bit easier, but if you like long division, feel free to do it. It becomes a problem if there starts becoming larger powers and you need to use placeholders. Is this function even, odd, or neither? Well, our test for that is to plug in a negative x. Our function's not f, our function's h. So h of negative x is 4 times negative x to the 4th minus 3 times negative x squared. Well, what do we get? We get 4 times a negative to an even power is going to be positive. Negative to an even power is going to be positive. What do we notice? We got back the original function. So that makes it even. If you plug in a negative x and you get back the original function, it's an even function, which means it's symmetric about the y-axis. It has symmetry if I reflect it across the y-axis. You could graph it and you would see that it would be symmetric across the y-axis. So this is the last lesson of Unit 1. We've covered so much about polynomial functions. Hopefully this video helps because our test is coming up soon.